You might not imagine how amazing and fascinating gravity really is. Welcome to Enigma Files. In the last episode, we talked about the greatest mystery of the universe, time. This time, we're going to dive into another big mystery of the universe, gravity. Gravity is currently regarded by physicists as the most mysterious and fascinating force that we still can't fully explain. Let's start by discussing the history of gravity. Gravity was actually discovered over 2,000 years ago, but people still didn't have a correct understanding of it. The first person in history to have a relatively accurate understanding of gravity was Galileo. Over 400 years ago, Galileo discovered an incredible property of gravity. No matter what the object, whether heavy or light, or what material it is made of, the force of gravity acting on them is the same. So, he dropped two iron balls of different sizes from the Leaning Tower of Pisa. To his surprise, both balls hit the ground at the same time. However, we don't actually know if Galileo ever did this experiment. This event was recorded by Galileo's student, Vincenzo, in Galileo's biography, but none of Galileo's own writings mention it. So some people doubt whether the experiment, even if it happened, was actually performed by Galileo. But no matter who did it, the fact is that the weight, material, and shape of an object don't matter. Whether it's a grain of dust, a feather, or an iron ball, if there's no air resistance, they all fall to the ground at the same time. Though this phenomenon was discovered at the time, no one could provide a reasonable explanation for it. Later, Newton explained it with an apple. When an apple fell on his head, he suddenly realized that the apple was being pulled by the Earth's gravity. Newton then understood that everything on Earth is subject to this force, and it's not just Earth. Anything in the universe exerts a gravitational pull. It's not just the Earth pulling us. We also exert a gravitational force on tables, chairs, and even between two people. This force was called universal gravitation. At that time, Newton was brilliant. He figured out the law of universal gravitation after being hit on the head by an apple. He believed that the Earth's gravity was the reason it could hold onto the moon. This revelation, just like Einstein's later work, sparked a revolution in understanding. Before this, scientists knew the Earth orbited the Sun, and the Moon orbited the Earth, but they didn't know why the Earth orbited the Sun or that it had anything to do with the apple falling. But Newton explained this through universal gravitation. Later, Newton also gave us the mathematical formula for universal gravitation, and when scientists used this formula to calculate the orbits of celestial bodies, they found that all of them followed the law of universal gravitation perfectly. At this point, universal gravitation and Newton became famous. Everyone believed that Newton had solved the mystery of the universe. However, with the advancement of observation technology, astronomers discovered a celestial body that didn't conform to Newton's formula for universal gravitation: Mercury. By observing it, they found that Mercury's orbital period didn't match the period predicted by the formula. The difference was about 50 seconds every 100 years. Though this difference wasn't large, it couldn't be eliminated no matter how much the measurements were refined. And it wasn't a measurement error. This anomaly caused people to reconsider the idea that universal gravitation could explain the workings of the universe. Later, another problem emerged that directly challenged universal gravitation. It stated that only objects with mass would exert a gravitational pull. But scientists discovered something without mass that was still affected by gravity: light. Light has no mass, but it can be pulled by a black hole, swirling around it, and even falling in without being able to escape. This is very strange. Why would something without mass be attracted by gravity? According to the universal gravitation formula, objects with no mass shouldn't have any gravitational force and shouldn't be pulled by gravity. So in this case, universal gravitation completely breaks down. Who solved this problem? Einstein. Einstein's understanding of gravity was completely different from Newton's. First of all, Einstein overturned Newton's views on time and space. Newton believed time and space were absolute and unchanging, but Einstein believed that time and space are flexible. They can stretch or compress. Another crucial point is that Einstein believed that speed and gravity are equivalent. For example, we humans need gravity to live normally, but in space, there is no gravity, so we float. If we want to live in space for a long time, we need a rotating spacecraft to simulate gravity through centrifugal force. This is using speed to replace gravity, and the two are equivalent. To us, there's no difference. So in Nolan's film Interstellar, when they were traveling to Saturn and had to fly for 2 years, they couldn't do it without gravity. Therefore, when they reached space, they started spinning the spacecraft so they could live inside it, just like on Earth. This way, they could sleep for 2 days and still reach Saturn. But they couldn't look out the window because of the spinning, which would make them dizzy. In the future, if we want to colonize Mars or other planets, we'll need this technology. The greater the mass, the slower time goes. The faster the speed, the slower time goes. Einstein's theory perfectly explains why Mercury's orbital period doesn't match the predictions of Newton's law of universal gravitation. Mercury is so close to the Sun that it experiences a huge gravitational pull. As a result, time on Mercury is much slower. So what we observe as a slow movement of Mercury may actually be much faster. Once we factor in the time dilation, the results match the calculations. Later, when the period of Mercury's orbit was recalculated, it was found to match the observed data. One more thing. Einstein believed that universal gravitation does not require both objects to have mass, because gravity is not a force at all. He proposed that mass bends space itself. As a result, objects near a massive object will move along a curved trajectory due to the bending of space. So, the Earth doesn't orbit the Sun because of an attractive force between them, but because the Sun bends space, and the Earth simply follows this curved path to avoid falling into the Sun. Since gravity is essentially space curvature, it doesn't matter whether an object has mass or not. As long as there is a curved space, any object, whether massive or not, will follow that curved path. This explains why even light, which has no mass, bends around massive objects. Because Einstein's theory of relativity could explain things that Newton's theory couldn't, Newton's law of universal gravitation was dethroned, and relativity ascended to its pinnacle. Einstein also made a significant contribution by predicting the existence of gravitational waves. Gravitational waves occur because gravity causes space to warp. So when an object with gravity moves through space, it creates ripples in space, just like a ball moving across a water surface creates ripples. However, these gravitational waves are extremely weak. Even massive objects, like black holes or neutron stars, only create small ripples. These waves are detectable only when supermassive objects like black holes or neutron stars collide. Even then, because of the vast distances, these waves are very faint by the time they reach Earth. In 2015, after nearly 100 years since Einstein's prediction, scientists in the US detected a gravitational wave from 1.3 billion light-years away, caused by the collision of two black holes. This confirmed Einstein's theory, proving that space is indeed flexible and can ripple. The detectors used in this experiment were enormous, each with two 4-kilometer-long arms, and there are two such detectors, one in the northwest and one in the southeast of the US. These detectors worked together because the wave was so tiny that both sides needed to detect it to confirm its existence. The project began in 1992 and took 23 years to build. Once it was ready in 2015, the first gravitational wave detection occurred immediately. Since then, the instrument has detected 10 gravitational waves. It turns out that black hole collisions are more frequent than expected, suggesting that black holes are abundant in the universe. The fact that gravitational waves are detected from black holes colliding shows how incredibly difficult it is to observe these collisions directly, as black holes don't emit light. Interestingly, the team of scientists that made this discovery, including Kip Thorne, who advised the film Interstellar, won the Nobel Prize in Physics in 2017. Normally, Nobel Prizes are awarded many years after a discovery, but in this case, the award came very quickly after the discovery in 2015 and the public announcement in 2016. While this experiment reinforced Einstein's theory, relativity is not perfect. One major issue with relativity is that it cannot explain singularities, points where mass is infinite. Einstein's theory can't handle the calculation of infinite values, and even if it could, we can't observe a singularity directly to confirm the results. This gap in relativity was something Einstein himself could not resolve. In fact, in his later years, Einstein denied the existence of black holes. Why is it so important to resolve the issue of singularities? Because a theory that explains the entire universe must be complete. If there's a known celestial body that can't be explained, it means the theory has a flaw. A truly universal theory would explain all phenomena, indicating that the universe follows a single set of rules. If those rules exist, the future would be predictable, just as we can predict tomorrow's sunrise based on the established pattern of the past. This predictive power depends on the laws of nature being consistent. If singularities defy relativity, then the future cannot be determined, and causality breaks down, meaning that causes would no longer necessarily lead to predictable effects. If there is an exception to the rule, then the formula isn't complete, even if it can explain everything else. This is why Newton's law was dethroned. It couldn't explain black holes, light, and other cosmic phenomena, and so it couldn't explain the universe's overall laws. Einstein sought to create a theory that would explain everything, but if singularities don't follow his theory, it can't offer a complete answer about the future of the universe. Sadly, we can't observe singularities directly. They are hidden within the event horizon, beyond which nothing, not even light, can escape. But is there a way to see a singularity? Theoretically, if a naked singularity exists, one without an event horizon, we might be able to observe it. However, none have been found so far. This brings us to another physicist, Roger Penrose, who won the Nobel Prize in Physics in 2020. There were 3 scientists awarded that year, all for research related to black holes. British physicist Roger Penrose was one of them. If you don't know him, you may have seen something he designed, the Penrose staircase, a staircase that appears to be continuously rising and looping. He designed the staircase, which even appeared in Christopher Nolan's Inception. Penrose proposed a hypothesis to fill the gap in relativity regarding singularities. This hypothesis is called the cosmic censorship hypothesis. Penrose believed that the universe has a sort of censorship mechanism. In this mechanism, the universe has a censor that makes sure anything not conforming to the laws of the universe or anything unreasonable, such as a singularity, becomes invisible or is erased. Penrose believed that the universe can audit every corner, determining where things follow the rules and where they don't. If something doesn't follow the rules, it will be hidden or erased. This hypothesis essentially suggests that if the universe indeed has such a censorship system, then the future of the universe is determined and causal relationships are fixed. For example, time travel or events like grandfather paradoxes would be impossible because they would break the laws of the universe, and the universe would eliminate them. In simpler terms, Penrose's hypothesis suggests that humans can never truly know whether a singularity conforms to relativity, because the universe doesn't want us to know. If we try to figure it out, we will be erased by the universe. The universe only wants us to accept that everything else fits the rules. The universe wants us to think that way, preventing us from defying its laws. Penrose also said that there are indeed bare singularities in the universe, with one being the singularity at the beginning of the Big Bang. This singularity would have been bare because there was no event horizon and it exploded, no longer existing in its original form, which is why we can no longer find any bare singularities today. Now, what is causality? Some might not fully understand this. Causality means that the cause determines the effect, or in other words, the past determines the future. If causality holds true, the future is fixed because the past is fixed. For example, when we calculate something with a physics formula, we are essentially predicting the future. We design a car, build a building, calculate their speed, weight-bearing capacity, etc., to know what will happen in the future. Our theories, our knowledge, all aim to determine the future. If the future were not fixed, then why would we calculate anything? All physical formulas would be meaningless. Einstein was determined to find the formula that would allow us to know how the future is fixed. He believed that the future is determined and that he needed to find the relationship between the past and the future. Once this relationship is found, we would know everything about the future. All scientists and physicists base their research on the assumption that the future is fixed. The future is not uncertain, and this is the current understanding based on our philosophy, physics, and scientific theories. To put it more simply, when we eat, we do so to avoid hunger in the next few hours. If we didn't know whether we would be hungry later, we wouldn't eat now. Back to the topic of gravity. Physics today believes that there are only 4 fundamental forces in the universe: the strong force, the weak force, electromagnetic force, and gravity, the so-called gravitational force. The strongest force is the strong force, and the weakest is gravity. The strong force operates within atomic nuclei, holding protons and neutrons together, even though protons are positively charged and should repel each other. The strong force overcomes this and binds them tightly together. To break an atomic nucleus apart, you need to use a particle accelerator like CERN's Large Hadron Collider, which can achieve speeds close to the speed of light. The weak force is a force that can change the properties of quarks. Nuclear radiation comes from the weak force, which can cause atomic nuclei to decay. This is also a very powerful force, but it has a strange, almost magical quality to it. The strong and weak forces act within atomic nuclei, but in everyday life, we don't feel them. The forces we do feel are the electromagnetic force and gravity. Any force other than gravity is considered electromagnetic force, such as when you give someone a push. That's also electromagnetic force. These 4 forces are all the forces in the universe, but they have entirely different natures, so they cannot be described by a single physical formula. Imagine these 4 forces as 4 cosmic gems: the strong force gem, the weak force gem, the electromagnetic force gem, and the gravity gem. If you put them all together, you could snap your fingers and create a universe. This also implies that in the early universe, these 4 forces were actually one force. The Big Bang caused them to separate into the 4 distinct forces we know today. If they were originally one force, then logically, there should be a single formula that could describe them. Scientists are currently searching for that formula, hoping to unify these forces. Once they succeed, we will understand the singularity and how the universe was created. We could even create a universe ourselves. Actually, about 60 years ago, the weak force and electromagnetic force were already unified under a concept called electroweak interaction. Now, scientists are working on unifying the electroweak interaction with the strong force, and only after that will they consider unifying gravity. Because we understand the least about gravity, and it is the weakest of the 4 forces. Gravity only becomes apparent at large scales, such as with something as massive as Earth. A pyramid wouldn't generate significant gravitational force. You wouldn't feel any pull just by standing next to it. So why is gravity so weak? This is very counterintuitive. Gravity permeates the entire universe. The mainstream theory in physics today is that gravity is weak because it is the only force that can transcend dimensions. This means that no matter in how many dimensions we exist, gravity acts the same in all of them. Because gravity acts across all dimensions, it gets spread out, which is why gravity feels so weak in our dimension. Kip Thorne also believes this. In Interstellar, for example, the protagonist communicates with his daughter in the 3D world by using gravity, because gravity is the only force that connects different dimensions. He used gravity anomalies in a 4-dimensional world to send binary codes and Morse code to NASA's coordinates, and also transmitted data from the black hole to his daughter. There's no other way. Light wouldn't work because it would be sucked into the black hole, but gravity waves can escape. This is the strength of gravity. It's both incredibly strong and incredibly weak. If we discover areas where gravity behaves abnormally on Earth, it could very well be a way to communicate with other dimensions. And the only way we could interact with other dimensions is through gravity. But we don't yet have the ability to control gravity. The first step in controlling gravity is anti-gravity. So, what is anti-gravity? If you're interested, feel free to leave a comment, and we'll make a dedicated video on anti-gravity later. If you enjoyed this video, don't forget to like and subscribe.